Thank you again, Admiral, and I want to introduce our next speaker, and that's Professor Terry Hughes. He's Director of Australian Research Council's Centre of Excellence for Coral Reef Studies, headquartered at James Cook. He's a great leader in terms of coral reef's response to climate change from bleaching, a finder of practical solutions to these issues. He's been dubbed the Reef Sentinel by the international science journal Nature for his global role. That's a global role in applying multi-disciplinary science to reef sustainability. He's director of the ARC Center. He's a former editor of Coral Reefs. He's been the chair of the 12th International Coral Reef Symposium. He's here today with us. We're very proud to have him. So Terry Hughes, welcome, and we look forward to hearing your insights about the coral reef situation.
Thanks. Yep. Thanks very much. Well, it's a pleasure to be here, and I really enjoyed the first talk. So you've heard a U.S. perspective, a NOAA perspective. Now you're going to hear more of an Australian perspective, and it's probably appropriate for me to remind myself, as well as you, that about 400 million people around the world depend on coral reefs for their livelihoods and food security, and the vast majority of them live in relatively small, relatively poor, often rapidly developing nations. And for them, the global decline of coral reefs, which we're all aware of, really hits home because they depend on reefs for their food security, for their livelihoods to a much greater degree than wealthy folks like you and me. So I'd just like to make that as a kind of opening statement. I'm going to talk about the responses of coral reefs in Australia and throughout the tropics to global warming. Global warming due to burning of fossil fuels and changes in land use over the last half century is the most prominent element of anthropogenic climate change. There are three other elements that I won't talk about today, and those are, very briefly, an increase in climate extremes, like the frequency and intensity of hurricanes, ocean acidification, which is an end-of-century problem under current business-as-usual emissions of greenhouse gases. The primary one I'm going to talk about today, I'm also going to leave out rising sea level, which is a problem for coastal real estate and insurance companies, but it's not so much of a problem for corals. In the aftermath of what has now been the third global coral bleaching event, it's pretty clear that heating is the number one climate change issue impacting on reefs, and that's the one I'm primarily going to talk about today. I'm going to start out with a little movie clip. It has no sound, so I can explain what you're looking at. It begins with me sitting in a small airplane, which will prove that I don't always wear a suit and tie. That's the Great Barrier Reef, about 150 feet below this low-flying aircraft. Those are the flight paths that we took in 2016 and again in 2017. This is what a heavily bleached reef looks like from a helicopter, again at 150 feet. Everything that's white or yellow in this picture is basically a dying coral. And in 2016, about 700 of the 3,500 individual reefs that make up the Great Barrier Reef looked like that in terms of the severity of bleaching. Underwater, severe bleaching looks like this. These white corals are bleached. This one is bleached and dying. It's now been colonized by filamentous algae. Most of these corals are staghorn corals in the genus Acropora. That's another one that's just died. What is bleaching? It's a breakdown in the symbiotic relationship between a coral host and microscopic algae called zooxanthellae that live inside its tissue. A bleached coral is energetically compromised because it's not receiving the photosynthesis from the zooxanthellae, the microscopic algae. And the normal narrative in the literature is that bleaching is not necessarily fatal if the depleted population of zooxanthellae regrows inside the coral and it regains its color. Most of the color that a coral has comes from its zooxanthellae. We found something different, however, in that it didn't matter what strain of zooxanthellae these corals had, because the bleaching was so extreme that half of the corals that died did so in the first week after the peak summer temperatures. So they didn't die slowly of starvation because of too few zooxanthellae, or at least many of them didn't. Mortality from bleaching is actually very complicated. We saw more disease of post-bleached corals. We also recorded a huge increase in per capita predation by snails and crown of thorns starfish on the depleted coral populations afterwards. So this is an outline of my talk. I'm going to start out by talking about heat exposure as a driver of large-scale ecological change. Then I'll talk about the coral bleaching record throughout the tropics over the last 40 or 50 years. And finally, at the end of the talk, I'll try and be a little bit more upbeat and talk about the prospects of recovery of the Great Barrier Reef, which is our current focus of research in Australia. By way of introduction, let me show you this graph. This is temperature anomaly. Think of it as temperature increase in degrees centigrade over time. From before 1900 up to the present day. I'm sure you're all familiar with temperature anomaly versus year graphs. They're usually shown as bar graphs, where there are negative blue bars on the left side showing it used to be a lot cooler, and taller red bars on the right showing global warming increasingly towards the present day. This is a little bit different in that it's a regression with 3 types of data points. The different symbols here represent different phases of ENSO cycles. So I'm sure you're all aware that El Nino phases in most parts of the world are slightly warmer during ENSO cycles. Then we have ENSO neutral years, and finally La Nina phases, where temperatures in most parts of the tropics are a bit cooler. The main point of this graph is that temperatures are rising throughout ENSO cycles. And if you look at the data points for cooler La Ninas today are warmer than El Ninos were in the tropical ocean 30 or 40 years ago. So in the course of my career, I've been a marine biologist for 40 years, beginning with my undergrad. In the 1960s, 70s, up to the early 80s, regional and certainly global scale bleaching was unheard of. Then we first saw a regional bleaching event in the strong El Nino period of 82, 83. The first global event affecting 70% of the world's coral reefs wasn't until 1998. And we've just seen the third global bleaching event. The second was 2010, and the third was, depending on how you measure it, between 2014 and 2017 in different parts of the world. So the gap between the first bleaching event in the early 80s and the next bleaching event, on average throughout the world, was 25 years. Since 2010, that gap has shrunk to just 6 years. So the frequency of these bleaching events is increasing and the gap between them is shrinking. And that gap, of course, is critically important because it's the window where recovery can take place. And it takes about a decade for the fastest growing Indo-Pacific coral assemblages dominated by those staghorn corals that I showed you earlier. It takes about 10 years for them to have a decent recovery after a major disturbance. This is a map of the tropics and subtropics. It's got 100 locations on it with these different color dots. 70 of them are red, indicating that in 2015 and 16, 70% of these 100 locations experienced severe bleaching, which we've defined as affecting more than 30% of the corals. 30% of the corals went white. For most of these locations, this was the third or fourth time they had bleached. So of these 100 locations, only 6 have not yet bleached since 1980. The other 94 have all bleached on average 3 or 4 times, and some of them, like French Polynesia, has just bleached for the 9th time in March this year. So what happened in 2015 and 16 is the northern reefs bleached in the northern hemisphere summer, and then 6 months later in early 2016 they bleached in the southern hemisphere, and equatorial reefs often bleached twice in both of those two years. Conservation biologists put a lot of store in spatial refuges, which are special places that don't bleach. But we're down to only 6 out of 100 that haven't yet bleached severely, and all 6 that didn't bleach severely in 2015 and 16 have bleached relatively mildly, usually multiple times in recent decades. So the world is full of former potential spatial refuges as more and more of these places are bleaching, and increasingly for the 3rd, 4th, or even 5th time. And here's a graph showing that. This is time on the x-axis, and this is the cumulative number of the 29 World Heritage listed coral reefs around the world that have bleached. So far, 93% of them, 27 out of 29, have now bleached at least once. That's the 1998 global bleaching event, which bleached many of them for the first time. So only 2 of the 29 have not yet bleached severely, and we expect them to bleach very, very soon. The Great Barrier Reef has now bleached 4 times. So it bleached in the first global event in 1998, but not before. Then we were very unlucky to have only a 4-year gap, because the average gap following 1998 was closer to 20 years. And then we had a huge gap of 14 years where we escaped exposure to high levels of heat. And then, unfortunately, we've just experienced the first back-to-back bleaching event on the Great Barrier Reef in 2 consecutive summers. The climate modelers tell us that back-to-back bleaching will become routine. In other words, it'll happen every year by about 2040, 2050, depending on the trajectory of greenhouse gas emissions. That's kind of an academic endpoint, because by the time we have bleaching every year, there'll be 0 time for recovery, and reefs, if we don't do something about emissions, will probably cease to exist. This is the map of the Barrier Reef, and I put this in as well as the movie clip because I need to remind you of the scale of it. It's 2,300 kilometers long and up to 250 kilometers in width. If that was Miami, then Boston's about there, and this would take you into Canada. So it's a huge piece of real estate. It's 344,000 square kilometers, which is the size of Japan or Italy. So it's a big system to study, and we put a lot of effort in responding to the bleaching event to study the system-wide changes that have occurred now on the Great Barrier Reef as a consequence of the back-to-back bleaching. So I used a plane or a helicopter. We flew the helicopter for 3 days up here in 2006. I didn't use it again in 2007 because it crashed, and my wife wouldn't let me get back on it. Before I go to the next slide, I need to explain to you the standard metric of heat exposure. This is work we've done in extensive collaborations with NOAA, who have the satellites that tell us with high levels of precision what the temperature was, the heat exposure was on all these different individual reefs up and down the coast of Queensland. So the metric we use is called degree heating weeks. So if you think of a spike in temperature above the long-standing summer maximum temperature, measure that in degrees centigrade, and then multiply that by the duration of the spike. So 8 degree heating weeks could be a 2-degree anomaly above the long-standing summer maximum that lasts for 4 weeks, or it could be 1 degree that lasts for 8 weeks. So it's a metric that integrates the height of the spike and the duration of the exposure. Bleaching has now become so commonplace that we actually have weather forecasts for it, issued by agencies like NOAA and the Australian Bureau of meteorology. And I'm sure you've all seen the maps that have different colors of pink and red that predict the likelihood of bleaching in coming weeks or months. When NOAA issues those weather forecasts for bleaching, it accompanies it with what they call an advisory, which says if you get temperature exposure of 4-degree heating weeks or more, you'll see bleaching. And if it goes above 8, you're highly likely to see coral loss, coral mortality. So those two thresholds, 4 and 8, are familiar to anyone who works on coral bleaching. It turns out that the empirical basis for those two numbers is pretty slim. And so NOAA were really interested in our large-scale bleaching data as a way of ground truthing the accuracy of the 4 and the 8-degree thresholds, and I'll come back to that in a moment. This is from the first paper that we published on the 2016 bleaching event. We're very lucky in Australia to have these two historical maps showing the pattern of bleaching. The top 3 maps are where the bleaching occurred. So red is severe bleaching and green is no bleaching. And you can see the footprint of each of those 3 events. I'll get to 2017 in a few minutes. Is different. It was very much a coastal pattern in 1998. There was more bleaching further offshore in 2002. After the first 2 bleaching events, we thought maybe the northern Great Barrier Reef is a spatial refuge. It's the most remote part. That little knob there is a town called Cairns, which is a tourist resort, but there are very few people north of Cairns. There's very little fishing. There's not much. There's no coastal development. It's as wild a place as I know of. In the coral reef world, lots of sharks and dugongs and crocodiles. We thought its wilderness status might have afforded it some level of protection from bleaching, and boy were we wrong, because in 2006 the northern half of the Great Barrier Reef pretty much fried. So from Cairns north, that's about a 700-kilometer stretch up to Papua New Guinea in the north. We saw the most severe bleaching event we've ever recorded on the Great Barrier Reef, and the south escaped. The south escaped because a cyclone came along. So you may recall in February 2016, Cyclone Winston crossed Fiji as a Category 5 system, and it killed lots of people there. It came to southern Queensland 10 days later as an X-cyclone, as a rain depression, and it brought the temperature of the southern half of the Barrier Reef down by nearly 3 degrees centigrade. It rescued it. Now, if you think about that, that cyclone demonstrates that the entire Great Barrier Reef could have bleached because of extreme heat exposure, except for the vagaries of local weather. We also had a cyclone in 2017, but it came a month too late in the wrong place, and it was Category 4, so it caused huge damage. Increasingly, people like me are wishing for a cyclone. As the temperature goes up and up and up, you need to be careful what you wish for. The bottom 3 maps are NOAA's data, which show the heat exposure. So these are, no pun intended, heat maps of 5-kilometer squared pixels of degree heating week data from satellites. And I think you can see the correspondence between where the heat was in each year. In 2016, the northern Barrier Reef was up to 3 degrees hotter than the normal summer maximum temperature, and it stayed that way for typically 5 or 6 weeks. So we had degree heat exposures in the north of 12, 14, 16, which is quite extreme. And in the south, it was much cooler. So we saw no bleaching in the south. You could think of all of the data points on this map being plotted against all of the data points on that map as a regression. And that's what I'll show you next. So while I was in the helicopter and the airplane in 2016, we put about 100 people underwater for a month. And underwater, you can you can measure much more precisely the level of bleaching. You can measure it as a continuous variable from 0 to 100% of the corals affected. You can identify the species. There are 350 species of corals on the Great Barrier Reef. And we went back to all of these locations 8 months later to see who had survived and who had died over that time frame. So this is the first of several coral response curves that I'll show you. In each case, the x-axis will be the same. It's degree heating week exposure from NOAA's data. And on this axis is something that the corals did. In this case, it's the percent of the corals that bleached, and you can see this asymptotic curve. By the time we got to about 10 or 12 degree heating weeks, 80 or 90% of the corals were bleached. That's a very high level of bleaching. The surprising thing was the threshold where bleaching began was only 2. And by the time we get to 4, which is NOAA's advisory, we actually had about 50%, 45% of the corals were bleached at the threshold. So those 4 and 8 numbers obviously depend on variables like the species composition and on the naivety of the corals. When were they last exposed to a blast of heat? In the case of the Barrier Reef, these were naive corals that hadn't been exposed to extreme heat for 14 years, since the 2002 bleaching event. And Acropora, which are known to be heat sensitive, were the dominant corals, as they often are throughout most of the Indo-Pacific. So the 4, and I'll show you the mortality threshold in a minute, were too high in 2016. The corals were more sensitive than we thought they were going to be to this level of heat exposure. We went back to these reefs underwater after 8 months. We were shocked and probably horrified as well at the high level of mortality that occurred instantly. So at the scale of the Great Barrier Reef, 15% of the corals, that's many billions of corals, died at the peak of the summer temperatures, and another 15% or so, bringing the total to 30%, died over the ensuing 8-month period. Most of that loss was from cairns north, where the average reduction in coral cover was 61%, and there was no mortality in the southern, cooler part of the Great Barrier Reef. So this is, unfortunately, a fairly typical picture 8 months after the 2016 bleaching event. You can see these dead table acroporas, dead bushy acroporas, dead staghorn acroporas. In the background, you might make out this brain coral. It's lost tissue on its top, but there's remnant tissue that's looking a bit ragged around the sides of the colony. And in the back here, there's a big, massive Porites colony, big, slow-growing, mound-shaped coral. It's pale, which is unusual because Porites are tough. They can live for hundreds of years, and to achieve that longevity, they've got to be good at surviving most sources of mortality. So crown of thorns starfish don't like to eat them. They're very good at dealing with sediment. They're resistant to cyclones, and they don't normally bleach. But in 2016, they did, and some of them died. Even 100-year-old corals died at a much lower rate than these more heat-sensitive acroporas. So bleaching is actually incredibly selective, and in the bleaching literature, people use the terms winners and losers. That terminology typically refers to who bleached and who didn't bleach. So we've measured the ultimate losers, which is actually who died and who didn't after 8 months. And you've already seen this map. This is the thermal exposure, and this is the pattern of mortality that we measured underwater. And you can see the correspondence between them. In the southern third of the Great Barrier Reef, there was little bleaching and no mortality. In the middle, about 10% of the corals died. And north of cairns, the average mortality rate was 61%. The scale of that mortality is obviously very large. It's about, whoops, sorry, what have I done? It's about 700 kilometers from the tip of that map down to about there. So the scale of damage from this one bleaching event was 10 times bigger than the normal scale of damage from a cyclone or a hurricane that crosses the Great Barrier Reef, and I'll come back to that issue in a moment. So I showed you one coral response to degree heating weeks in terms of bleaching. This is the response curve in terms of mortality. So this axis is degree heating weeks again. This is the change in coral cover on a log scale. So minus 100 means they all died. 0 means none of them died. So with no heat exposure, we saw no losses, which is what you'd expect. By the time we got to 4 degree heating weeks, we had an average of 45% loss of corals. And by the time we get to 8, we had 60 to 90% decline. So obviously the 8 degree heating week threshold didn't work very well in 2016 because, as I've explained, probably because of the naivety of these coral assemblages, which were dominated by heat-sensitive acroporas. I'm going to talk just very briefly about the winners and losers issue. That's a big Porites again, which did bleach, but it regained its color and survived. That colony there grows about 1 centimeter a year, so it's about 300 years old. This picture comes from the Maldives, where severe bleaching occurred for the first time in 1998. I took that photograph about 15 years later, and it shows a lagoonal thicket of acroporas that has never recovered following the 98 bleaching event. So bleaching has the capacity to change quite dramatically the mix of coral species, and that has implications for the future vulnerability of reefs as this assemblage structure, the mix of species, changes through time. I hope that's not for me. Okay. And then the unimaginable happened. It bleached again the following summer. So I've already shown you the northern bleaching in 2016. In 2017, the heat stress was concentrated in the central part of the Great Barrier Reef. We saw some bleaching in the north, but nothing like year 1, and we saw even less bleaching in the south. So maybe 10% of the corals bleached in year 1 in 2016, but none of them bleached in 2017. This back-to-back bleaching allowed us to address a couple of new research questions, one of which was, did the memory of what happened in year 1 affect the outcome of heat stress in 2017? And it turns out it did. The Australian Bureau of Meteorology wrote a report on how sea surface temperatures in 2016 were the hottest they'd ever recorded in 100 years of records. And they had to do it again in 2017 because 2017 was even hotter on about 85% of the Great Barrier Reef. And despite year 2 being hotter, we saw less bleaching in year 2. Most of it was in the middle part of the reef. And there are a couple of reasons why that pattern occurred despite the bigger intensity of the heat, which is shown in this slide. So this is a map of the Great Barrier Reef showing the difference in degree heating weeks between year 1 and year 2. So anything that's a warm color here, yellow, orange, or red, was hotter in year 2 compared to year 1. Only that far northern inshore bit was a bit cooler in year 2. Despite it being hotter in 2017, this bleaching response curve moved way to the right. So I've already shown you this pink response. So it's degree heating weeks against likelihood of bleaching. It took a lot more heat in year 2 to generate the same level of bleaching and mortality as year 1. So in year 1, NOAA's 4 and 8 degree thresholds were too low. In year 2, it was the opposite. I think I said that the wrong way around, but anyway, they were either too high or too low in the 2 years. There's a couple of different mechanisms going on here. We didn't see that shift in the central part of the Great Barrier Reef because the heat in year 2 was so extreme, history didn't matter. In the north, we saw much less bleaching, despite it being mostly hotter in year 2. And the reason for that, I think, is that dead corals can't bleach twice. So the acroporas had 80 or 90% losses north of about there in year 1, and they simply weren't there in huge numbers in year 2. What was there is those big Porites bommies and brain corals and tougher corals that don't bleach as easily, and when they do bleach, they tend to regain their color a few months later and survive. A different mechanism occurred in the south. So in year 1, we had degree heating weak exposures of 2, 3, 4 in the south, which triggered about 10% bleaching. In year 2, it was warmer, and we should have seen about 20 or 30% bleaching in the south, and we saw none. So it appears that the prior exposure to very modest elevated temperatures in year 1 had some protective effect when the corals were subsequently exposed to slightly warmer temperatures in year 2. So to summarize all that up, the impact of the second heat wave in 2017 and where it occurred depended on the history of bleaching 1 year earlier. And that means we no longer have the luxury of studying these bleaching events as if they're one-offs. We actually need to understand them better as sequences of rapid fire and highly interactive events. And that's a research challenge that we're now having to grapple with. And the other point I'd like to make is that the resilience of reefs is increasingly being challenged by these new disturbance regimes where we have the ongoing historic regime of a cyclone with a return time of maybe every 30 to 40 years. Superimposed on that now is these increasingly frequent and much larger scale bleaching events. The corals have evolved to cope with cyclones. They can either resist them through a massive morphology like the big Porites I showed you, or they can rebound quickly like the acroporas do by early reproduction, producing lots of baby corals. They've evolved to cope with cyclones. They have not evolved to cope with increasingly frequent large-scale bleaching events. So between the 2 years, we lost 49% of the corals on the Great Barrier Reef, overwhelmingly in the north in year 1 and in the center in year 2. The spatial scale of that loss is about 1,500 kilometers in extent from the northern tip to the southern boundary of the bleaching in year 2. That's about 10 times bigger than the footprint of a Category 4 or 5 cyclone that crosses the Great Barrier Reef. And that's important for regeneration of the reef. The track of a cyclone is typically 50 to 100 kilometers wide. That means there are undamaged or lightly damaged reefs nearby, north and south of that track, to replenish the damaged populations. But the spatial scale of the damage from the bleaching is an order of magnitude bigger. And to make matters worse, the current on the Great Barrier Reef flows from the north to the south. So the southern undamaged populations are not going to be able to reseed the depleted central and northern populations. So I've talked about these two. I'm now going to change tack and talk very briefly about the prospects for recovery. We have measured coral recruitment at the scale of the Great Barrier Reef many times, I think 7, before the back-to-back bleaching occurred, and we've now measured it twice since then to look at shifts in the composition and density of baby corals. And here's 2 photographs. This one taken in 1994 when we first deployed settlement panels like this along the length of the Great Barrier Reef. The difference between the 2 photographs is this settlement panel is surrounded by the adult broodstock, producing lots of larvae, and this one isn't. It's kind of lonely because there's very few adult corals in the vicinity. So these are standardized sampling devices, if you like. We put them out 10 days before the annual spawning event, which is highly predictable. We put them out synchronously along the length of the Great Barrier Reef on the 10th day, plus or minus 1, before the spawning, and we pick them up 8 weeks later, again synchronously, over a 3-week window. It's logistically challenging. We need 5 or 6 boats with about 30 people on board to simultaneously deploy them at the scale of the eastern seaboard of the United States. When corals reproduce, they can do it in one of 2 ways. They can brood larvae. So brooded larvae are large, well-developed. They're already equipped with zooxanthellae, and they go splat, which is a technical term meaning they have a short larval duration. They settle within half a day, usually. So at the scale of an individual reef, there's 3,500 of them. Brooded corals are self-seeding. So the connections between the stock and the recruit are very short. Spawned corals, which is about 85% of the species, including almost all the acroporas, have much longer larval durations. They kick out eggs and sperm, which fertilize externally, and they're not capable of settling for at least 4 days, sometimes 7 days after fertilization. So they go further. They go tens, maybe 100 or 200 kilometers. Their connections are much larger. So a switch in the proportion of brooders versus spawners would have huge consequences for the way the Great Barrier Reef is interconnected and for the transport of larvae. So to make a long story short, this is the pattern of recruitment before the bleaching, and this is what happened afterwards. The diameter of each of these circles is proportionate to the density of coral recruits per panel. So a big circle means a panel had 200 baby corals on it. They settle at very high densities when the adult broodstock is intact. And the blue wedge is the proportion that are brooders. So historically, spawners predominate, and the average density per panel is somewhere around 50 to 100. Afterwards, when we looked at these new panels, they often had no recruits or just 1 or 2. So for spawners in yellow, we recorded a 93% decline in recruitment in 2018, the first summer after the back-to-back bleaching. For brooders, it was about a 30% drop. So for the first time, the proportion of brooders and spawners has flipped, and brooders predominated in 2018. So I talked earlier about the filter in the species composition due to the winners and losers who survived. This is another filter, because as these corals grow and mature, the shift in the mix of baby corals is going to affect, not necessarily one-to-one. When they grow up, they're going to change the species composition of the adults that they grow into. So we're busily measuring the recovery trajectory of the Great Barrier Reef. We're not quite sure where it's going to recover to. It's not going to go back to the original coral assemblages because we lost many 50 and 100-year-old corals, and we simply won't have that length of time before the 5th bleaching event occurs, almost certainly in the next El Nino event, if not before, and will change the mix of species even further. The silver lining is that the Great Barrier Reef is now a glass half full as well as half empty. So we lost half the corals. The mix of species has changed quite dramatically. It seems unimaginable that the mix of genotypes within each species has also not changed. The reef has gone through one hell of a natural selection event. And the new assemblage of corals are tougher than the old ones. You may recall the most recent IPCC report that came out from South Korea last November. It summarized some recent climate modeling which projected that a 1.5 degree of global warming would kill off 70% of the world's coral reefs, and 2 degrees of warming would irreparably damage 99% of them. I think those numbers are too high. And the reason I'm saying that is those climate models assume that a given level of heat exposure, let's say 8-degree heating weeks in 2050, will have the same effect as 2040, 2030, 2020. And our results from 2016 and 17 show that that's not true. It took a lot more heat in 2017 to generate the same level of bleaching and mortality as 1 year earlier. So I'm often asked this question by everyone from the media to high school kids to politicians, and I wrote a paper about it. It's a 9-page review published in Nature. Half of these authors are social scientists, and I compiled this team to help me write this paper, which is about the coral reef crisis. And there's a huge emphasis currently on growing new corals, on coral restoration. But I think the problem is deeper than just growing more corals. It's actually a crisis of governance. And we need to think about the effectiveness of institutions, of policy frameworks, of legal frameworks. We need to think about social norms and human behavior. And all of that jargon is not my field. That's the field of social science. And I think we need a lot more coral reef social science in order to navigate the coral reef crisis. But my answer to that question is a cautious, optimistic yes, but they will be very different. The Great Barrier Reef today is already a highly altered system. It still has many tens of billions of live corals, but the mix of species has changed quite profoundly in the top 2/3. The southern third is now incredibly vulnerable. It's got about 50% coral cover, 80% of which is thermally sensitive acroporas, and when its luck runs out and it gets 6 or 8 degree heating weeks, most of that acropora will bleach and die. So the future of coral reefs depends on this trajectory, and this is from the IPCC report that I mentioned. So the left half of this graph shows the accumulating greenhouse gas emissions, primarily from 3 types of fossil fuels and from land clearing. And this is the trajectory we need to achieve in order to limit global warming to another 0.5 degree, to reach the 1.5 degree target of the Paris Accord. And that, to me, is the real challenge in terms of securing a future for coral reefs. So to sum all that up, I've shown you data that says that recurrent bleaching is now the new normal. Coral reefs have already changed forever. It's very poorly documented at a regional or global scale because most of the monitoring programs, including the monitoring of the Great Barrier Reef, are based on total coral cover, where all species are combined. We don't have regional scale data, except some of the stuff I showed you, on the mix of species, their relative abundance, and how that's changing really rapidly at a global scale. But tens of billions of corals are still alive. On the Great Barrier Reef, they're the tougher ones, and I think our management challenge is to secure the future of those survivors rather than an emphasis on restoration. So reducing emissions and local drivers is absolutely critical. The Australian government has now given $100 million for coral restoration on the Great Barrier Reef. It includes projects like fans on one reef to cool a square kilometre of the 344,000 square kilometres, cloud brightening, floating sunscreen to shade the corals, coral gardening, assisted evolution, assisted migration, the whole 9 yards. I estimate it would cost $25 billion to replace the corals that died in 2016 alone. So 100 million is not going to go further than a couple of hectares. And I'll leave it at that. Thank you very much.
We do have some time for questions, so if you have something for Dr. Hughes, and I think we have online as well, but let me know if we do.
Hi.
Terry, Chris Langdon. It's a multi-part question. You said that some of the corals died within just a week.
Yeah.
And that made me wonder if what was the actual temperature anomaly? Was it many times warmer?
It's about about 3 degrees.
3 degrees?
Yeah.
So not that much more than usual? Or was that acceptable?
Well, corals typically bleach with 1 degree above their normal summer maximum, whatever that is. So it's, as you know, it's not an absolute temperature. It's the anomaly that matters. So they're locally adapted to whatever temperature they normally experience. If you go 1 degree above that for longer than a couple of weeks, they start to bleach. We saw 3 degree temperature anomalies in the north in 2016 and in the center a year later.
Because the second part is that the difference in the relationship between 2016 and 2017 in terms of coral loss and degree heating rings could be explained if the temperature anomaly was significantly different in the 2 years, and it's not so much the product.
Yeah,
it's really more the temperature.
You're right. I haven't looked at that. So I simplified the degree heating week exposure to a one spike, but often there's multiple spikes. And there's a paper published by one of our postdocs, Tracy Ainsworth, in Science about a year ago, where she experimentally exposed corals to a spike in temperature to mimic an early summer short-lived heat wave, then let them cool down to normal temperatures and expose them again a couple of months later. And the initial exposure had a protective effect. And she looked at the genomics of that. So heat-tolerant genes were being turned on. So the experience at that time scale of a few months mattered. And we now have people doing experiments at a longer time tail to look at the 12-month history of 2 back-to-back summers bleaching. Yeah. Hi.
One online question. When you were comparing the 2016 bleaching with the 2017 bleaching, 2017 had higher temperatures but a lower bleaching percentage. Did you find any evidence of the zooxanthellae reshuffling to a more resistant clad as a result of bleaching that occurred in 2016?
Did everyone hear that? Okay. We haven't seen any evidence of large-scale shifts in the clades of zooxanthellae. And as I said, the instantaneous mortality meant that the zooxanthellae didn't matter. The corals simply cooked. Whether they had thermally tougher zooxanthellae in their tissues or not was kind of irrelevant. Mortality post-bleaching is actually very complicated. So it's not the simplistic, they die slowly of starvation because of too few zooxanthellae. Disease prevalence went through the roof, and the per capita predation on the remnant acroporas in the north also increased tenfold. So if you're the last acropora on the reef, all the predatory snails and other coral predators aggregate on you, and you're toast. So it's quite complicated. So whenever anyone tells you X% of the corals died from bleaching, you need to know the start date, because they might have missed the instantaneous mortality if they start too late, and you need to know the end date because it keeps rolling. So I showed you mortality after 8 months, and that increased over the following year. When a coral bleaches, it still typically has about 20% of its zooxanthellae in the tissue. And so the recoloring of a coral is almost always the regrowth of those remnant zooxanthellae. So there's no swapping. Swapping has mostly been demonstrated in laboratory where multiple strains of zooxanthellae are exposed to a coral. There is some field evidence, but it didn't occur on the Great Barrier Reef. Do you want to field the question? Yeah. Joan?
So I was just wondering, obviously recruitment is the most important part in the recovery process, and in some areas you have much higher mortality than in other areas. So I'm wondering if you, now that you're looking at recovery, if you have found that there's some sort of a threshold necessary for the recovery of a certain location to happen. Having said that, I know that you have broadcast corners, and obviously the dispersal will mean that this larvae can be coming from other areas. But since the region that has bleached so heavily is quite large, I'm wondering if you're finding some sort of a pattern and what needs to be there to allow recovery, at least in 100 kilometers for some areas to recover.
Okay, there's quite a few issues there. You started off by saying that recruitment is the driver of recovery.
One of them.
Yeah, it's one of three. So the other two are the remnant corals, some of which were damaged and had lost tissue. They're now mostly fully repaired, and they're regrowing. And in terms of improvement in coral cover, that process is far more important than the arrival of tiny babies. We also found that juvenile corals from cohorts that settled a year or two before the bleaching survived better than the adults. And that's been recorded elsewhere in the literature. It may be related to their semi-cryptic nature. Baby corals, as you know, often settle in nooks and crannies or on the sides of things, so they're partially shaded. And that seemed to have afforded them some level of protection. So those older babies, if I can use that term, are now about 5 or 6 years old, and they're growing rapidly and promoting the growth. I didn't show you another result from our recruitment study, which was the relationship between the loss of broodstock adults and the change in recruitment. We did that separately for the brooders and spawners. It turns out there's a straight line correlation between the two. So a reef that lost 90% of its spawning adults had a 90% drop in spawning recruitment. So the corals are fecund, they're reproducing as normal. There just aren't enough of them to produce the same level of recruitment. But every spawning season is trillions and trillions of larvae. So even 7% of trillions is a very large number. So we redid the recruitment in 2019. And on Lizard Island, where recruitment had dropped by 99%, it increased 300% to 3% of the historical average in 2019. So we're at the beginning of a trajectory of recovery of recruitment, which will then drive a longer trajectory of recovery in adults as those babies mature. The chances of that being interrupted by the 5th bleaching event is very high. I'll let you do it.
I'm Curtis Gray.
Hi.
I have a question about the pattern of bleaching and mortality that you saw. Did you see the potential for a reservoir from bleaching at depth?
Yeah, we looked at that. So most of the data I've shown you is from relatively shallow habitats. The aerial bleaching, for example, we distinguished 5 habitats when we scored the bleaching intensities. So crests, flats, lagoons, upper slopes, and there was one other I can't remember. We did do depth profiles, and there's 2 published papers on that now. They both show that bleaching diminishes with depth because there's an interaction between the heat and the light. But even at 40 meters, there was substantial bleaching. So it's not a spatial refuge. It's an attenuation with depth. I would love to show you a map of the Great Barrier Reef of what happened at 40 meters, but it was beyond our capabilities. Yeah. Hi.
Yes, you mentioned this 16, 17 back-to-back bleaching.
Yeah.
This phenomena happened only once in the history or record or anywhere else?
It's the first time it's happened on the Great Barrier Reef. The first regional scale bleaching event was recorded in 82, 83. Much smaller scale bleaching events have been recorded in the literature going back to the 1950s, but they're very local, and they're attributed to something like a flood or a freezing event where you've got icicles on the oranges in Florida. You can make a coral bleach in the laboratory by torturing it in any number of ways. So it's a stress response. But regional scale bleaching, where half the Caribbean bleaches, or bleaching across the Indian Ocean, that's a modern phenomenon as far as we know. People have looked in the growth bands of corals for synchronous stress bands in the annual growth increments of massive corals like the Porites I showed you. So what you're looking for is synchronicity across a population of cores taken through the corals at some half-decent spatial scale, 100 or more kilometers. There's a nice study of that from the Mesoamerican Reef, which showed a synchronous stress band in 1998 and none before that, going back a century or longer in the growth bands of the corals.
And also the heat wave, the impact on mortality of coral reef, we discovered this is a local event. Is this a global event as well, just a locally, how spread is over?
Be careful. Australians might be insulted if they thought you meant the Great Barrier Reef was local, because it's the world's biggest coral reefs. Yeah. No, the map of the tropics that I showed you with the colored dots said that 70% of them severely bleached in either 2015 or 16. So it was by any measure, a global event. Yeah. Hi.
I'd like to extend on Matthew's question a little bit by asking about the fossil record. We know there's been a number of glaciations that have descended on the northern and southern hemisphere over the last 100,000 years.
Yep.
Have the paleontologists given us any evidence of this kind of extirpation of coral reefs as a prediction
No.
of what's going on that can be used if we stand back?
The short answer is no. So the most useful fossil record, I think, is quite recent. It's before the last ice age. So it's extant species of corals that are still alive today. So in that warm period, temperatures were warmer globally than they are now, and sea level was higher. So on the west coast of Australia, there are fossil reefs. They're about 125,000 years old, of modern corals. They're near Perth, so they're 800 kilometers south of the southern limit of those same species today. So in warm periods, reefs expand and species migrate into the subtropics as temperatures rise, and we're seeing that around the world now. So tropical fish are overwintering for the first time in Sydney Harbour. Corals in the Caribbean are migrating up to the Carolinas. They're migrating along the Ryukyus chain towards mainland Japan, and in some cases displacing kelp beds with new coral beds. So that kind of mobility has been well documented. We don't have any fossil evidence that I'm aware of paleo bleaching events.
Can this be used, this historic evidence, as evidence in the predictive ability of, well, we're not just guessing with all our mathematical models, we've actually seen it happen before.
Yeah.
This is when when Japan went underwater or something like that.
Yeah, so in the review paper I mentioned, corals in the Anthropocene, we used the term the climate gauntlet. So I think it's going to get very rough for corals over the next century or so. And there's a big question mark about what future temperatures will equilibrate at. We're almost certainly going to miss the 1.5. If we go to 3 or 4, then people will suffer hugely. So I don't think we will get to 3 or 4. We'll be somewhere less than that. When it equilibrates, corals will probably have a catch-up period where they adapt to the stabilized temperature and regrow what will probably be by then highly depleted populations. So I'm cautiously optimistic that that's a likely trajectory in the future. But the climate gauntlet implies that things are going to get worse before they get better.
gentleman here has a question.
Hi.
So with the increase of bleaching events and prevalence of anthropogenic stressors, have you noticed anything in the Australian government with them being more receptive to ecological complaints, or is economics the only way that you can get things through to them?
Yeah, the management agency for the Great Barrier Reef is called the Great Barrier Reef Marine Park Authority, and they produce a report every 5 years. It's required under legislation. The latest one, which I reviewed, it's 300 pages long, included lots of our results, and it concluded that climate change is the #1 threat to the Great Barrier Reef. This is an official federal government report, and that the outlook for the Great Barrier Reef has been downgraded from the last report 5 years ago from poor to very poor. So at that level, there's an acknowledgement that climate change is the #1 issue. But unfortunately, our government's policy is to increase the country's emissions and open new coal mines and new gas fields. So Australia's emissions have been climbing for the last several years under our current government, which repealed an earlier law that put a price on carbon emissions. That law was working, the emissions were going down, but when it was repealed, it was a perfect before-after experiment, and they're still rising. The main reason they're rising today is fugitive emissions from fracking.
Take one more question, then we probably could break and do informal questions. Karen.
So you had mentioned this $100 million that's being floated towards these projects and some very novel ideas that are being trialed for that. How are those decisions getting made? How do they decide which projects are getting that money and which ones, by being very novel, may have a really high possibility of failure?
Okay, I could talk at some length about that, but I won't. Governance of the Great Barrier Reef has 3 tiers. So the state of Queensland is involved on certain issues. The Commonwealth or federal government is the main level of oversight. And then we also have UNESCO, because it's a World Heritage Area. So the Commonwealth government promised UNESCO a few years ago that they would give $500 million of further revenue towards better protection of the Great Barrier Reef. The context for that was UNESCO were considering putting the Great Barrier Reef on the endangered list, which they have not done. In order to spend $500 million quickly, because they promised to do it by the end of 2019, they didn't give the money to a Commonwealth agency, which would have been the logical thing to do. But had they done that, it would have had to be spent in annual increments, and they needed to spend it instantly. So they gave it to an NGO with 6 employees, $500 million. That NGO has an advisory board which is made up of the CEOs of fossil fuel industries. So to answer your question, they're in charge.
Well, on that somber note, I think we'll take a break, but we have our 2 guests.